Utah since 2000. And oh, we're getting recorded too. All right, excellent. That's all right. And I've been involved in this software project called FEBio, which stands for Finding Elements for Biomechanics and Biophysics. So I thought I'd just start off and ask how many people here are familiar with the finite element method. All right, great. So most of you. So that's maybe a little loud, Ed. But I won't have to go over that stuff. So I'll just go ahead and get started. So, in physics, we often have to think about these partial differential equations that govern, conservation of mass, momentum, and energy. And oftentimes we're interested in solving problems such as fluid mechanics or solid mechanics that give rise to different PDEs. And so each of these PDEs kind of has its own area of specialization, like the Navier-Stokes equations for incompressible fluid mechanics, or balance of linear momentum, which is what we deal with in solid mechanics, et cetera. And so, obviously, PDEs, unlike ODEs, it's pretty difficult to come up with analytical solutions, and there's only a few simple geometries. So that's where we use numerical methods. And since all of you know about the finite element method, you know that this is one of the most common ones. It's been around for a very long time, and it's used throughout engineering, especially in aerospace industry and auto manufacturing, things of that nature. Today it's used in nearly all branches of engineering, throughout solid and fluid mechanics, but also electromagnetism, heat transfer, coupled multi-physics problems as well. And it's even used in computer graphics and computer animation, as in the Avatar movie. And so there are a bunch of different variations of the finite element method, and it's not going to be too important for what we talk about today. But the motivation for our project was that although finite element method's been around for a long time, in terms of the field of biomechanics, historically we were stuck using either closed box commercial software such as ANSYS or Abacus, or codes that were somewhat open, like Nike 3D, for instance, or FEBio. But generally speaking, our options are were pretty limited. And there were a lot of downsides to using these codes. In terms of capabilities, oftentimes, back when we started this project, these codes just didn't have a relevant constitutive models for biomechanics and biophysics. So to describe biological materials and biomaterials, many times traditional engineering constitutive laws don't work. The commercial codes are closed source, so it's difficult to verify what they're doing or to expand them. The codes that were semi-open source, like FEBio and Nike 3D, were extremely poorly documented. In fact, there's actually an interesting story behind a related code called Dyna 3D. So Dyna 3D was an explicit dynamics code developed at Lawrence Livermore Lab by John Hallquist. And so he spent a lot of time working on that code. And then it got to be a point in time, I think it was in the late 80s or early 90s, where the national labs were really pushed to provide their codes to the public. Right? Before that, everything was just confidential. It was like nobody could access it. And so the developers, including John, were kind of down about this. They felt like they were giving away all their intellectual property, but yet they were forced to release the source code. So they went through and stripped out all the comments out of the source code. And so you just had thousands and thousands of lines of Fortran 4 with no comments. And so then they said, here, there it is. We've done it, And so a lot of times when we looked at those codes back in the late 80s and early 90s, they literally had no documentation and no comments. And so that was a challenge. And so the other aspect of either of these categories of codes is that they just were simply not tailored towards the biomechanics community. They didn't have the kinds of things that we needed for reproducibility in research, to disseminate our results and share our models, et cetera. And so we decided that at that point that we wanted to put together this alternative that would be ultimately open source and available to the community, called FEBio. And so it's a collaborative effort between my lab at the University of Utah and Gerard Ateshian's lab at Columbia University. And a big part of the project here at the University of Utah is our lead software engineer, our lead code developer, Dr. Steve Moss. And Steve's been instrumental in this project from the very beginning. So it started around 2005, and we started to think that what we wanted to provide to the community was something that was kind of turnkey, so that they didn't have to compile code if they didn't want to. It was just going to be ready to use and rich in the features that they needed. And so we've kind of built the project around three pillars. First, again, we're trying to target the biomechanics and biophysics communities specifically. So this is not like a code that was designed as general purpose or for the aerospace industry or something like that. It would be freely available and easy to extend. And we would have thorough documentation, and provide support and outreach to the community as much as we can. When we first started the project, we had very limited support to help people outside of our groups, but that's gotten better over the years as we've continued to get new funding for the project. So this is kind of a history of the project. So as you can see, right after the Big Bang, Steve Moss joined my lab. Okay, and so since then, in 2007, we released the first version of the code. A big milestone for us was getting an actual grant to support the software effort in 2009. So we got an R01 from NIH, and we've actually had that same grant for the entire time since 2009. And we're in year 3 of the, year 18 of the grant, year 3 of the current renewal, and so hopefully that could continue to go well over the years. We've, added new features, we've added new capabilities, and that's where we are now. And so one of the things that's really been very gratifying about this project is the degree of impact that it's had, which we never would have anticipated, 15 years ago. We've had over 70,000 downloads of the code. We have over 16,000 registered users on FEBio.org. So the way that we track use statistics is we require people to set up an account there. And once they have an account, they can download all of the installation packages for whatever operating system that they have. We have a forum with 1,500 users. This number of publications is around 800 now. And there are probably 20 to 25 different instructors around the world that use FEBio in their coursework, including myself. So, and this graph on the bottom just kind of shows the growth in the downloads and the number of registered users over the years since we started the project. And so the key features in the code, we started off just focusing on nonlinear solid mechanics. That was the first thing we worked on in 2005. And then when Gerard joined the project a year later, we started to add capabilities for biphasic materials, which are mixtures of solids and fluids, and sometimes poroelasticity is another term you'll hear used. And so Gerard extended that to multiphasic mixtures. And then in the last 10 years, we focused on adding a new fluid mechanics solver and FSI solver. You can also simulate systems of chemical reactions in FEBio, both between solutes that are in the fluid phase and solid-bound molecules that are attached to the solid skeleton. You can do heat conduction, steady state, and dynamic solvers as well. The multiphasic part of the code is kind of one of the, I would say, the most unique aspects of FEBio. So we think of a multiphasic material as consisting of a solid, which can have multiple pieces itself. It can be a mixture of different components. And then there's a fluid that fills up the pores in the solid. And that fluid or solvent can have neutral or charged solutes in it, okay? And on the solid side, you can have molecules that are bound to the solid phase. And so, as I mentioned, you can have chemical reactions that occur between the solutes and the solid-bound molecules, which you can use to simulate things like growth, remodeling, cellular signaling, cytokine signaling networks that involve the extracellular matrix, degeneration, et cetera. You can simulate osmotic and charge effects as well, all fully coupled to the nonlinear equations of conservation of linear momentum. And so we have a plugin framework that allows you to extend the code. I'll talk more about that. We've spent a lot of time over the years developing constitutive models, especially in the solid mechanics sides of things, with a strong focus on representing anisotropy, damage, fatigue, and failure of, again, biological materials. It's really easy to add custom materials to the software, as I'll talk more about. And of course, there's a whole set of boundary conditions and loading conditions that are kind of general ones, like displacement or pressure, but then more specific ones that are related to the physics in the code. And so, so in terms of the scale, since you're already familiar with finite elements, kind of that we're using a continuum approximation. The physical scale can range anything from looking at cells all the way up to whole body response. We can look at tissue deformation, stress, growth, and remodeling. And we can simulate different types of chemical reactions. So like diffusion and transport is a subset of what we can do in the code now. And so we have all sorts of different anisotropic constitutive models that we can implement, and we can have the material properties of the materials affected by growth and remodeling as well. If we want to model skeletal muscle or cardiac muscle, we have various models for active contraction. These are also useful for modeling cell mechanics. So cells exert forces on the extracellular matrix. And so these force fields can be simulated within FEBio. And as I mentioned, you can have interstitial fluid transport and interfacial mass transport across interfaces. So if you can have, for instance, two multiphasic bodies coming into contact at a contact interface, and you can have mass transport across the interface that conserves mass. So we have a lot of different application areas among our users. Big areas for us are orthopedics and cardiovascular mechanics. Those two areas are very large, but there are a lot of other people that are using the code in tissue engineering applications, mostly in a research setting. A lot of people studying growth and remodeling and mechanobiology. My own group, we use the software to study angiogenesis and do some multi-scale modeling. And we have colleagues, for instance, Ross Ethier at Georgia Tech, who's very interested in studying aspects of ocular mechanics. And so this is just like a few example applications on the left here. This is just a cross-section through an idealized model of the left ventricle that's contracting. And so this just illustrates through the software that we can simulate not only active contraction, but the anisotropic properties that cause the heart wall to twist as it contracts. This center model was developed from Ben Ellis's group. He's a research faculty member within our department, and he's focused right now on studying spinal mechanics, cervical spine mechanics in children, especially children that have various defects in the growth of their spine. This is a picture up top here from our first fluid mechanics solver, and this down below is from our FSI solver, which was published several years ago. And so there's kind of a variety of different physics that you can model. In my own lab, we couple FEBio with a growth model for blood vessels, and we predict the growth of the vessels based on the density, anisotropy, and strain field in the extracellular matrix. And so the idea with this code is that we can predict the topology of microvascular networks and how that topology is affected by various biophysical factors that are represented in FEBio. And so this is another example application from Professor Gerardo Teshian's lab. So he's collaborating with a biomedical scientist there to understand renal cystogenesis. So there are certain types of kidney diseases, generally hereditary, that result in the formation of cysts in the kidney. Polycystic kidney disease is one of them. And so he and his colleague had questions about the growth, like what were the factors controlling the growth? Was it, like, for instance, circumferential contraction? Was it radial shortening? And so they went through and did an entire matrix of different simulations to figure out that only when the mutant cells contracted along a certain direction, followed by proliferation, could they simulate kind of the outgrowth that you see exactly that mimics the cyst growth. And so this is just another image here showing, again, in this case, the relative volume of the cyst as it grows outward. And again, this is a symmetry model. Okay. And so, as I mentioned in my own research, we often are interested in what controls the guidance of the growth of angiogenic microvessels. And so one of the studies that we've done in my lab is we developed this core and field model of angiogenesis, where you seed angiogenic microvessels in a collagen core, and it's surrounded by a field, but there's an interface that forms when you polymerize the two collagen gels, and that interface is denser and has aligned fibers. And so we can show that when you simulate, when we see this in the experimental side, we can simulate the same behavior, which is that unless there are cells that migrate from the core into the field, most of the angiogenic vessels grow just within the core and won't cross that interface. But using a combination of experiments and simulation, we were able to demonstrate that the reason that they will migrate outside of the core when you have macrophages present is that the macrophages actually find their way across the interface and lay down a plume of VEGF. And so there's this chemotactic signaling that will then cause the vessels to cross the interface. And so this just demonstrates that you can couple FEBio with other software packages and capabilities, exchange information, and do various types of multi-physics modeling. And so we started out with three software packages. Actually, we started out with just FEBio, the solver, at the beginning. And then eventually we said, we really need a pre-processor and a post-processor. We're tired of using the stuff from Lawrence Livermore. It's terrible and not documented and not supported. And so we developed preview and post-view. So we had kind of 3 programs. And it was like that for probably 12 or 15 years or something like that. And just like about 3 years ago, we decided, let's put this all into one package. And so we developed this framework called FEBio Studio. And so FEBio Studio is essentially a user interface where you can do both your pre-processing, your post-processing, and you can launch your finite element jobs. And you can either run your finite element jobs locally on your local workstation, or you can set them up so that they will run remotely, like in a Slurm queue or something like that. And so this provides a little bit more flexibility and a single integrated environment. And this has actually tremendously helped our software development, because now instead of writing, basically having 2 UIs that we have to keep updated, we just have this one UI that does everything. And now when we distribute FEBio, we just distribute a single installation package that installs FEBio Studio and the FEBio solver, depending on which software platform we're on. And so in this environment, you can do everything that you need to, starting off from building models, to running them, to visualizing them, animating, and looking at the results. And so the workflow is very similar to other finite element codes. We need to define a finite element mesh. So sometimes this starts from image data in biomechanics. Sometimes it might start from a CAD model. And we don't try to reproduce a lot of the capabilities of codes like mimics or a mirror or anything like that. We assume that, if you're working, say, from medical image data or biomedical microscopy data, that you have some way to segment that image data and produce a closed surface. And if you can get that closed surface available, then we can import that, and then you can mesh it within FEBio and refine the mesh and do everything else. And so all of that kind of stuff is under the hood in FEBio Studio. The next step, once you have your model geometry defined, is to define the materials, the boundary conditions, whether you're going to have contact or rigid material, and then, of course, the parameters that control the nonlinear analysis. So we use quasi-Newton methods most of the time for solving the nonlinear equations that emanate from the weak form of conservation linear momentum. And so there are certain solution parameters that need to be specified to keep the nonlinear solver on target. So then we call FEBio. You can monitor the progress within FEBio Studio, or you can just go have a cup of coffee, or maybe take a vacation, depending on how big your model is, And then finally, when you're done, FEBio produces a couple of output files. One's a binary plot file database, another one's a text file, and those files can be analyzed within FEBio Studio. And so I can just open, hopefully FEBio will work on my machine. I'll get it open. Let's see here. Let me close this. Okay. See if I can find a model. I was gonna walk you through building a model, but then I realized that I don't have time. So I'm gonna pull one up that I already made. Okay. Let's see. Oh yeah.
It's like this adapter.
Sorry?
This adapters disconnect.
Oh yeah. You sure it seems like it's in right there. Still nothing? You got it?
No, it's still not working.
Okay. Okay, so I'll just get you oriented here. Let me see if I can just minimize this. There we go. Okay, so obviously you've got file open, file new model, etc. So I just opened a project that I'd already made. So this just consists of 2 objects. This yellow object on the top, which is a rigid body, and this kind of tan colored object on the bottom, which is defined as a Mooney-Rivlin material. And so over here on the left is the model tree. And so you can see the geometry of the different objects up top here. So you can see that there's one part here in object 2, et cetera, has 6 surfaces. And you can select any of these individual items if you want to. Or if you just want to, you can just click outside and unselect it. Once we get outside of the geometry, into the model itself, you can see there's some global parameters that are sometimes set. Like if you're doing chemical reactions or using multiphasic materials, then you have to enter some physical properties for that model. The other thing I'll mention is that there's an option to pick a set of units. And so that can be really handy. So by default, we assume that you are in control of the units. So whatever units for displacement and force that you pick determine the stress units. But you might want to work in like a common set of units in biomechanics, and then the software will calculate everything for you. So then, for instance, when you look at a constitutive model and the coefficients in that constitutive model and look at the properties, you can see that it will tell you what the units of those properties are, which is handy. So assigning a material to an object is really just as simple as selecting the object and then assigning that material. And so down here we have selections. So for each item, let me see if I can get that to open. There we go. So for each material, you have selections of items that can be added to it. So this material right here can be identified. The part can be identified by clicking on the arrow. If you have something that you want to add, you can just hit plus and it'll add it to that material, etc. If we look at material properties, so we can see that this is a Mooney-Rivlin hyperelastic material. And so because this material is compressible, we also have a bulk modulus defined for it as well. And then we have a density as well. And so, so one of the things that is kind of nice about the model tree is that you can see all the boundary conditions easily too. So in this case, we can see that there's a fixed displacement boundary condition. If we want to know where that's applied, we go to the selection, and then we can select the surfaces and hit the arrow. And we can see that it's on the outside edges of this box. Okay, so the top and bottom surfaces are free of boundary conditions. And we can see that these boundary conditions are X, Y, and Z displacement are fixed. Okay, so these are natural boundary conditions. Okay, and if we look at the contact menu, we can see that we have a sliding elastic contact defined. And again, if we go down and look at the surfaces, we have a primary side, and we can figure out which surface that is. It's the top of the box right there. And then if we look at the secondary side, we can select these surfaces and see that it's the bottom of the sphere. And so in terms of control of this model, since the top material is rigid, it has 6 degrees of freedom. And so we have 3 rotations and 3 translations. And so what I'm doing in this particular model is I'm just going to push the ball down until it contacts the box. Okay, so I just need to translate it in the -y direction. But the other 2 degrees of freedom for displacement and 3 degrees of freedom for rotation, I'm going to fix those. Okay, so those are defined via rigid fixed. And so if you go to this, you can see that for this particular rigid body, material 2, which is the only rigid body in this model, we have those values fixed. And then if I click on the displacement, we can see that the Y displacement tells it to go down 3 millimeters. Okay, and if we go down finally to the steps, so you can have multiple steps in an analysis, but this analysis just has 1 step. So for instance, you could step 1 might be you push the ball down. Step 2 might be you let it roll around on the surface or something like that. Okay, and so you can change the boundary conditions over time by defining different steps. Okay, and so if we look at this step, we can kind of see some of the information that's relevant to the analysis. So we have analysis type is static or dynamic, and the analysis type is tied closely to the physics modules that you're using. So right now, this model is set up to use the solid or the structural mechanics module, but we have these other modules, and if you pick one of them, it will expose solution options that are specific for that solution module. Okay, the FEBio uses automatic time stepper. So this is asking the software to take 20 time steps of 0.05, and this is a static analysis, so the 0.05 seconds is really arbitrary, but the termination time is a product of the number of time steps times the time step size, right? And since it uses automatic time stepping, it will adjust the size of the analysis as needed. There's some output information here that controls how many plot states are written, and then time stepper information for the linear system, asking, for instance, whether the matrix is symmetric. And again, all of these things are set by the default to the proper values for this particular physics. For the nonlinear solver, again, we're using a quasi-Newton method. And because this particular contact sliding interface formulation produces a non-symmetric matrix, we use Broyden's method in this case. and we can set some convergence tolerances and et cetera. And so if we want to run this model, we just come up here and click the run arrow, and it'll run it. And by default, the output from the solver goes down here into the screen right here. And so it's going to go through and run those 20 steps. And then when it's done, it's going to ask me if I want to load the results. And now what I see is I've got this little time thing here with discrete points during the analysis, right? And I can also animate this too. And if I don't want to look at the ball, I can turn it off. And I could pick a variable to look at. Let's say that I want to look at contact pressure, for instance. And so, so this gives you some idea of what's involved in doing a finite element analysis and post-processing. You can also select, for instance, individual nodes on the surface in this case and say, well, yeah, I want to know what's going on these nodes over time. And then you can use the graphing feature. And so in this case, we could take a look at contact pressure again for those different nodes. You can also make scatter plots. So you might be interested in, say, some variable, like for the selection for material 2, you can take the position, like I think it was Y, right? And then plot that versus force or something like that. And it'll show you that variable for the rigid bodies, okay? So that gives you some idea of the interface. We have all sorts of fancy visualization tools, everything from cutting planes, to vector plots, to tensor plots, to streamlines, to isosurfaces, to volume rendering, et cetera. And then, depending on what kind of analysis you're doing, you may be interested in using different tools there. For instance, in a fluid mechanics analysis, generally you want to look inside the mesh, right? So you're going to use a cutting plane, and then you're likely going to want to look at something like streamlines or particle plots, those kinds of things. All right, so maybe I'll just stop and ask if there are any questions at this point. Okay, yeah, hi. Can you visualize the output using virtual reality? I don't think so. I don't know too much about virtual reality visualization. Maybe you mean like on a big screen where you can walk around or something? Oh, that would be cool. Yeah, no, sorry, I don't know anything about that. Sounds cool though. Yeah. Okay, so let me just move on with the presentation. So, like I said, a big part of what we do is try to support the people using our software, and we've done that by putting together what I think is a reasonably nice web page with good documentation. Okay, and so when you go to our web page at FEBio.org, you'll find a section called Knowledge Base, and on there you'll see a bunch of tutorials just to get people started right out of the gate. You can get going with the software very quickly. And then the user manuals, we have theory, user manual, studio manual, and then developer's manual. And we have a bunch of videos from workshops, tutorials, case studies, et cetera. Let me just show you really quickly some of the stuff just so you get a feel for it. Computer's being a little sluggish today. Okay, knowledge base. So we spent a good amount of time on our user manual, tried to make it actually useful. And so, you've got a lot of detail here, not just on what to type in for the materials, but the actual equations that you're working with. And we always try to provide an example. And so that brings up a point I wanted to make, is that the input to a finite element analysis in FEBio is a text file. And so you can edit that text file in whatever text editor you want. So essentially what FEBio Studio is doing is it's producing that XML formatted file. Okay, and you can have multiple subfiles as well, so that can be kind of useful as well. In addition to this manual, there's also a really nice developer's manual. Let me see if I think that might be in my slides. Yeah, so I showed you the online manuals. The development manual is in Doxygen. And so if you're familiar with that, it kind of works in a combination of pulling things out of your source code. And then also you can add on to that. So in this case, for instance, this section I'm showing you didn't come from the source code, but it was actually written by us and inserted into Doxygen. Okay. We have a huge test suite in FEBio. And this verification suite is run every night on every platform. And so this is part of our CI/CD process. And so it compares the solutions that we get with known answers. And this is all run through GitHub Actions. And so it's all automated. And so we produce containers that run on AWS and test all the problems. You can check out the source code and compile it on there as well. We have longer problems that we run once a week. And one of the nice things about the test suite is it's available through our repository. So when you're in FEBio Studio, if you go to the project side of things, where am I missing it here? Let's see. I think it's just. I'm going to close this for just a second. I think I closed one of the windows that I need. Let's see. There we go. Okay, so you should see this tab at the bottom called repository. And if you click connect, it will ask you for your login information for febio.org the first time. But here's the test suite. And so this is everything that we run on our end. You can run any of these models on your end. You can open any of them up, take a look at them, and it'll just load them right in here. And you can see what that test problem looks like and what it's testing. The other thing that we do with the repository is we archive models that are associated with publications. And so primarily for our lab at this point, we're trying to get other people to do it as well. But like for instance, if you want to run the problems that were in our paper on reactive damage mechanics, you can just load one of these models. And you'll notice that this actually refers to that paper too. It's indexed into the paper. And so anybody who wants to can upload the models that are associated with their publications to help with reproducibility of your science. Okay, and so we felt this was a really important aspect of what we wanted to do with this project. And the other things that you'll find in here, in addition to the test suite, you'll find all of the problems that we put in the tutorial section of the web page, all of the webinar problems that we do for all the webinars, and any workshops that we run as well. And so between this, you can search for anything that you want. So like for instance, if you're interested in Tide Contact or something like that, you can find all the problems very easily that use Tide Contact. Okay, and so this can be really useful if you're trying to learn how to use a new feature. Okay, and so when you have an FEB file, you have the option. It'll download it, and if you click import as model, it'll pull it up in the interface. If you hit edit XML, it'll pull up in this format right here, which allows you to look through and see kind of a hierarchical list of everything that's used in that problem. And so this can be really useful for understanding the details of how the file is constructed. And there's a way to swap this back over to the standard text mode, but I forget what it is. So, all right, so let's stop there. Still got a few minutes here, so let's see what I can get through. Okay, this is an example of verification problem. I went through that. So we just talk a little bit about the software architecture since you guys are interested in those kinds of things. So, so we partition the software into multiple libraries, and so we try to make things as modular as we can. So for instance, we have one section called FE Core that has kind of fundamental finite element routines, and then we might have other modules that are focused on parsing the XML file, or maybe focused on biphasic mixtures. So generally, like we have one library for kind of each solver. So like for biomech, biomix, bioheat, et cetera. And so we also have this plugin framework, and I mentioned this earlier, and so I'll just go over it quickly. The idea here is that in FEBio, you can have plugins that are essentially dynamically registered and loaded at runtime. Okay, and so the reason you might want to do that is it helps with the development cycle. So you don't have to tie your development to the development that's going on in the main FEBio code. Okay, and so you can also choose at runtime which plugins are loaded. Okay, so if you want to use a plugin for a particular project, you can load it. If you don't need it, you don't have to load it. And this leads to faster development times. And there's all kinds of things that you can do with plugins. Most of the things that are listed here fall into the category of adding new features to FEBio. but the plugin interface also allows you to interact with FEBio from other software. So if you want to couple FEBio with another solver or something like that, this framework will allow you to do that. And so an example is that angiogenesis plugin that we use to model growth of blood vessels. And so we have one software package that controls the growth of those microvessels that are represented by connected line segments. And then that is coupled with FEBio, which allows the forces that are generated from those microvessels to act on the extracellular matrix, and also that so that the AngioFE plugin can query the properties, the biophysical properties of the extracellular matrix, like density and anisotropy, which control rate of growth. We use tensor class functions in FEBio. This isn't that new anymore, but when we started doing it 15 years ago, it was. So basically, if you wanted to find the stress tensor for a material, it's just one line. And coming from the old days of Fortran, this was kind of a relief to me. So constituent models, you can have solid mixtures. So within FEBio, a solid mixture can be any number of solid constituent models where the stress is additively, okay? I won't go through this too much. There are different analysis types, as I mentioned. And so structural mechanics is the one that we focused on so far today. But we also have the ability to analyze porous permeable materials that we refer to as biphasic analysis. Multiphasic materials, which I've talked about, where you can have charged solutes and solid bound molecules that undergo reactions. Fluid mechanics analysis, fluid structure interaction, where you can have, for instance, closure of a fluid domain that impedes flow, followed by opening, like as shown on the right here in this peristaltic pump. We've recently added capabilities for working with image data in FEBio. And so this allows you to import images into your model and query the intensity fields in the image and use those intensity fields to define, for instance, constitutive parameters or material properties or boundary conditions on your finite element model. So for instance, in the simplest case in biomechanics, we know that in the case of bone, the density of bone is related to the modulus, right? And so since CT queries bone density in Hounsfield units, you can use the CT intensity to assign a position-dependent modulus, right? That's one example. But there are a lot of other examples where we want to use image data in biomechanics. For instance, we often use sequences of image data for strain measurement. So we might spray a texture on a soft tissue and monitor its stretching over time to calculate its strain. So we're adding capabilities to do that type of digital image correlation within FEBio Studio. Similarly, we've added capabilities to measure anisotropy in image data. So typically, when you define an anisotropic material, you take one of a couple of approaches. You assume that the material has one or more preferred fiber directions. So like you say, the fiber family is running this way, right? Okay. Or maybe it's running this way and this way, okay? Two fiber families, right? The other approach that's become more common in the last 10 years in biomechanics is using an orientation distribution function that has some sort of parameterized function. So like ellipsoidal fiber distribution, okay? So the limiting cases there for the ellipsoidal fiber distribution are a straight line, right? Or a sphere, right? So if it's a sphere, all the fibers have equal probability in each direction, and the material is initially isotropic, but then once you start stretching it, the fibers realign, right? And so by having an ellipsoidal fiber distribution, you have this parameterized distribution of fiber probabilities that can be integrated to calculate the stress response from the fiber family. But you're still making an assumption about the distribution, right? When you measure a real distribution in a material, like shown here, for on the left, the collagen gel, or on the top right, the tissue engineered bone, what you'll find is if you look at the orientation distribution function here, it's plotted as probability is plotted as length of the radius. You'll see that this doesn't really look like an ellipsoid or a sphere or a line, right? And so what we've enabled in FEBio Studio is you can import image data and break it into subvolumes. And then for each subvolume, you can calculate the orientation distribution function using the algorithm that my student Adam Rofe invented. And so once you have that ODF, Adam's worked with Steve Moss and Michael Heron to create a way to integrate that ODF into the constitutive model, so you can model the exact fiber distribution at every point in the material. And so I think that I will stop there because I'm just about at 45 minutes. I just want to, I threw a bunch of stuff in here because I wasn't sure how long I was going to talk for. So I've got all sorts of good stuff, but here I'll just stop and thank the main people that I've worked with. Steve Moss, who I've worked with for almost 20 years now, and Gerard Atechian almost that long, Ben Ellis even longer than that, and Michael Heron, who joined the group about 3 years ago. And thanks for your time. I'd be happy to take any questions.
You have a question, grab a microphone nearby. One button underneath.
What happened to that little thing we throw around?
Oh, it's up there on the front row.
Okay. Does it still work?
Yeah.
Okay. All right. Jim's got a microphone. Is it working? Do you hear him?
One button.
Light on there.
Okay, it's all.
So my question is, do you do any the meshing in the FEBio, or do you bring all your meshes in from some other external package? And can you say a little bit about, like, are you using, like, what kind of elements have you found to be like best for what you guys are working on?
Yeah. So yeah, we have a lot of meshing capabilities in FEBio. There's kind of two approaches to meshing. One is using primitives in the software that are predefined, that have predefined topologies, and so those are really good for like test problems. Like if you need to make a block or a circle or something like that, it's great. So you just let me just. So if I want to create a block, I click on this. It asks me where I want the block and how big I want it to, and then it just makes the block. Then if I want to mesh it, I can control the mesh sections and hit apply, and it makes a mesh. And we have this for a lot of basic entities here, okay? But typically that's fine until you get to the point where you have a real model that's based on like image data or something like that. So at that point, the way that we approach meshing is to have the user import a closed bounded surface, okay? So any sort of like a CAD surface or a triangular surface that you can make, you can pull into FEBio, and we've coupled FEBio with two TET meshing software packages. One's called MMG, the other one's called TETgen. And so you can easily TET mesh objects. You can also do local refinement, de-refinement. You can refine based on a scalar field of your choice. We also have adaptive mesh refinement, like while the models are running, that you can use as well. So it's reasonably flexible. That said, there are times when I find that we prefer to make a mesh in some external software package for various reasons that might have capabilities. One of the things that we don't have yet is good capabilities for intersecting meshes and surfaces to produce, in the case where you have non-manifold objects. And so some of that stuff we'd like to do in some other software first. You had asked about element types. So we've got a pretty broad range of standard finite element types. We also have linear, quadrilateral elements, linear and quadratic elements for all of the tets and hexes. We've got three different types of quadratic tets and two different types of quadratic hexes. And then we have all the degenerated elements like penta and things like that. And so all of those basic elements are in there. One of the things we worked on quite a bit, I guess it was probably 7 or 8 years ago, was getting all of the quadratic order elements to work nicely with our contact interfaces. And so that took a little bit of reworking of the contact algorithms, but now, like, if you want to do like contact between two objects that have quadratic elements, it works really, really well. Yes.
I have a question. I apologize if it's maybe out of order question because I wasn't here for a while. We had to deliver the food.
Sure.
That's important. But I have a question about, so this is FEBio. So do you have any kind of direct pipeline between, for example, Slicer 3D and then basically importing the NRD files into FEBio directly and then meshing them, or?
So what you're talking about is Slicer 3D, which is a software that's designed for, primarily for segmentation, right? Yeah. So Slicer 3D, you bring in a volumetric image data set. You're able to segment it. You're able to make some geometric models in Slicer 3D, and that's kind of where things stop. And so once you have that, then you import it into FEBio Studio and mesh it. That would be the typical pipeline that we would use. And so we use Slicer 3D a little bit in our group. It's great software. And we have a collaborator that has built all sorts of extensions on the Slicer 3D. Then they import that geometry into FEBio Studio, generally create the finite element meshes in FEBio Studio. You can also import meshes too, right? So like if you are able to make a mesh in Slicer 3D or any other software, there's like 20 different file formats that we can import it as, you know.
Okay.
Does that make sense?
Yeah, because we had some problems with Slicer 3D and then meshing it in Cleaver 2, which is computer science department's
Yes.
measure.
Yes.
So it works fine, but if you want to do like, if you want to export, if you don't want to mesh, if you don't want to mesh it in Cleaver 2, there is no sort of way, like ANSYS doesn't accept NRD files because that's the main segmentation file coming out from the 3D slicer. So that's a must. So there is a direct pipeline between Slicer 3D. There is no need for Cleaver 2 or something like that. We can directly pull in the segmented geometry and then mesh it inside the FEBio.
Yeah, yeah. So if you're meshing with Cleaver, you can import the mesh from Cleaver into
Sure.
FEBio. I'll just mention that Cleaver was designed, the way Cleaver makes meshes works really well for objects with like kind of like fixed meshes where you're doing like electrical problems and things like that. But the way that it merges different materials together, the meshes that I've seen from Cleaver are not optimal for solid mechanics. They'd be more optimal for like electrical conduction type problems, you know. In solid mechanics, we really usually want smooth and refined meshes on the surface. And Cleaver is more designed to deal with the multi-material problem where the different materials are embedded within a volume, like a head or something like that, you know. So nevertheless, though, yeah, if you get a mesh from Cleaver, we can pull that directly in.
Okay, thank you.
Sure. Yeah.
Question, I was also hoping to try all this as well. Does this software allow for the ability to submodel? If you create a coarse model of a body, solve it, and you want to refine just the
And just refine a feature of interest and import the primary variable field from the previous solution as Dirichlet boundary conditions around it. Does it allow for something like that?
No, it doesn't support that. No.
Okay.
You know, if you're talking about refining the model, it means, you know, building a new mesh. Yeah.
Okay.
I was wondering how large the material library is and how easy it is to implement a new material.
Sure. Yeah. Let me just pull up the manual really quickly. Okay. So I believe it's chapter 4 is the material library. And so our materials are kind of classified based on the type, right? So under elastic solids, we have two main types. Uncoupled materials, which are used for nearly incompressible analysis, and unconstrained materials, which are fine for compressible case. And so, like for instance, if you go under uncoupled, I can't tell if this is loading or not. There we go. It'll give you the list of those materials, right? And so there's kind of the standard, you know, anisotropic and isotropic materials that we use in biomechanics. Like for instance, this Hallsepfeld gas or Ogden model is a really common model that people use for modeling arterial mechanics. Okay, so besides the uncoupled materials, if I can just go back to one page. There are the unconstrained materials, and you'll see a lot of overlap here because basically in one case, in the uncoupled materials, we're using a 3-field element that doesn't lock. And in the unconstrained case, we're using displacement-based elements, okay? And then we have fiber active contraction materials. And so like there's a lot of different ways to do contraction, but these ones are focused on skeletal muscle mechanics. And so these are contracting fibers that are based on calcium concentration, et cetera. And so the user can specify calcium versus time, for instance, to simulate contraction. There's also a force velocity based one where the user specifies like different components of the force velocity. Beyond those, we also have another class of materials. So that's all the elastic materials. So the fiber materials are kind of a similar setup where we have unconstrained fiber models that depend on the fiber stretch. And then we have uncoupled fiber models that depend on the deviatoric part of the fiber stretch. So if we look at the unconstrained models, since they're kind of similar, you'll basically see ways to model fiber families in anisotropic materials. So like, for instance, you can have a fiber with an exponential power law, linear response, and you have coefficients that define that. And so, and you can have like, fibers that are based on physical models of entropy, things like that. And the uncoupled ones kind of parallel that. So I don't want to go through all those, but under fibers, the idea is that these fibers can either be used by themselves as a fiber family, or they can be used as part of a fiber distribution, right? And so talking about fiber distributions, we have this framework called continuous fiber distribution. And essentially what you're doing is you have a strain energy for the fibers, and then you have a probability or an orientation density function, right? And then this is the Heaviside function. And so you integrate it over the unit sphere to integrate the probability of the fibers in each direction, right? And so like I said, like if the probability is a sphere, then initially the material is isotropic, but if it's like an ellipsoid or something, then you have anisotropy, and then as the ellipsoid deforms during the analysis, it changes the anisotropy, right? And so we have different distributions that you can pick. So like first thing you would do is say, okay, I want a fiber material model, like I want it to be exponential linear. Then you would say for distribution, maybe I want the periodic von Mises distribution, which looks like this, okay? And then once you picked a distribution, the last thing that you need to do is decide on the integration scheme. These are default values, but what we're doing here is we're sampling the unit sphere and to discretize the continuous distribution. And so there are different ways to do that optimally. Fewer points, the better in terms of cost, but more points, the better in terms of accuracy. So we try to put the points in the best place, So that's the fiber family stuff. And then once you get past the fibers, then you start to get into the viscoelastic materials. So we've got a couple of different viscoelastic materials in here. We have reactive viscoelasticity, which is a framework that Gerard Atessian developed, where the viscous behavior of the material is based on transformation of species from one type to another and breaking of bonds, okay? We have that, and we have various relaxation functions that you can use with reactive viscoelasticity. We have a framework of reactive damage mechanics that Gerard also developed. And so again, the idea here is that you have essentially chemical reactions controlling transformation of species from one material to another, which results in a weakening of the material, okay? Same kind of thing for reactive plasticity and elastoplasticity. We have multi-generation solids. Biphasic materials, essentially you can think of a biphasic material as having a fluid phase and a solid phase. So you pick one of our solid materials that I've already talked about, and then you pick a permeability model for the biphasic material. So like you could have constant permeability, we could have strain-dependent permeability, you could have anisotropic permeability. And then once we get past the biphasic materials, we start to get into the more complex things like triphasic and multiphasic. And so for those materials, you also have to specify things like chemical species, the concentrations, and charge, okay? And so then finally, with the multiphasic materials, you can define chemical reactions. And so you can say that a species A can undergo reaction with species B, say to produce species C. And so you can specify the initial concentrations or prescribe the concentrations and predict the values of those species, either in the solvent or as solid bound molecules that are bound to the solid phase, okay? And so we have, like, for instance, different reaction rate materials. You can have like a constant reaction rate, or there's another reaction rate that's we call the Huskies reaction rate, named after Rick Huskies, who was a person who studied bone adaptation and figured out that, based on the strain energy of the material, it determines how the density of the bone evolves over time. And so this idea here is pretty specific to bone, but the framework in FEBio is very general in the sense that you can have reactions depend in very arbitrary ways on the mechanics. And similarly, you can have material properties depend in very arbitrary ways on the chemical species. Active contraction, rigid bodies. We have homogenization. So I guess that's kind of gives you kind of like an overview. It's a pretty broad plate of constitutive models, and basically at this point, anytime anybody wants a constitutive model, we just add it. It's just easier for us to do it, but that's just because we have Steve Moss, right? And so like Steve can do it in like an hour. And so whereas like by the time one of us explained how to add a material, he could have already added it. So, I hope that answers your question. Yeah. Yes.
I was wondering, so for materials with
For materials that are nearly compressible,
Uh-huh.
I'm assuming you have it hard coded in the routine that it applies selectively reduced integration. If a user were to use the input their own material parameters, is there some switch where your solver will apply that if a Poisson ratio gets over a certain value?
Yeah, so actually the way that we deal with near incompressibility is that we partition the constituent models into two sets. One are the uncoupled materials, which are designed to be used with an alternative to the reduced integration called a three-field element. So in that element, we interpolate the displacement, nodal displacements, the pressure, and the volume ratio of the elements as separate field variables. So displacement is continuous between elements. Pressure and dilatation or volume ratio are discontinuous between elements. They're just continuous over the local elements and constant. Okay, and so anytime you pick an uncoupled material, you get the three field elements by default. Okay, you can override that, but you generally wouldn't want to. Like if you didn't need the three field elements, then you would just use the displacement based elements. Your other question was about adding your own material or material properties. And so if you add your own material, you can tell FEBio what the default element family is to work with those materials. Does that make sense? And so like if you add it as an uncoupled material, when you code the material, you'll be, let's just show you. Materials, plastic solids, uncoupled materials. You'll be using the deviatoric version of the deformation gradient tensor. And so this is like your standard uncoupled hyperelastic material. So you've got a term that determines the relationship between the volume ratio or the Jacobian and the pressure, and then another strain energy that depends on the deviatoric part of the right deformation tensor. Okay, and so if you define your material as uncoupled, then when you write the equation for the stress tensor and the fourth order elasticity tensor, those will be written already in terms of the deviatoric part of the deformation gradient. So, yeah, sure. Well, thanks for your time today. I appreciate it. Yeah.
Thanks again, Dr. Jeff Weiss. We've got food over here for that. Anybody who's interested in the scientific community club, scan the code. We're in our club, free. You never ask for anything other than attend whatever like this. Some workshops we're going to be putting together as far as dealing with some of the softwares that we offer here to teams. Analysis, SolidWorks. We're going to try to do a seminar on SolidWorks and help people that are coming up with prints. So when you want to have something like a test fixture made by the machine shop, it's not gibberish to them. It's not embarrassing for you. So yeah, thanks again. And thanks again for that question.